Hello, everyone. So today I'm going to present our FSE industry paper, which is titled A First Look at the Integration of Machine Learning Models in Complex Autonomous Driving Systems, a case study on Apollo. And this is the work that's mainly done by my master student, Peng, with collaboration with my colleague Jinqiu from Concordia and Lima from Kyushu University. My name is Tse-Hsun Chen, and you can call me Peter, and I'm an assistant professor from Concordia University in Canada. So in modern systems, AI is everywhere. So from self-driving car to social media, healthcare, and finance, this system, they use AI or more in particular machine learning to help them make critical decisions. So machine learning is becoming one of the core components of modern software systems. However, in such large-scale systems, machine learning is actually a small component. So in a study that's published in NeuroIPS in 2015, they found that at Google, only a small component is machine learning related within the large-scale system. So in this kind of large-scale systems, software engineering is an important concept to integrate the machine learning system to the system to other part of the system in large. Therefore, software engineering plays a key role in such AI-powered system in order to ensure the system quality and provide more functionalities. So in a nutshell, software engineering is crucial to ensure the functionality and quality of AI-powered systems. And in systems such as self-driving car, developers might use different code logic to provide more resilience to noises and to avoid some life-threatening situations from happening. Therefore, understanding how machine learning models interact with other machine learning models and how the models are integrated with the code is an important research area in software engineering in order for us to help further improve the AI system in general. So in this paper, we focus on studying the machine learning model integration with the source code and the model architecture in self-driving car systems. And we focus on self-driving car systems for three particular reasons. First, this kind of self-driving car system is one of the largest and most complex AI-powered system that's available. Second, this kind of systems, if not tested correctly or not tested thoroughly, can have some life-critical consequences. And finally, this kind of systems has a very large financial perspective and financial future. So a lot of companies, they have very strong interest into developing this kind of systems. So our goal in general is to understand how the machine learning model interact with each other and study their integration with their source code. And we hope that the finding can open new avenues or inspire future research on the practice of the quality assurance of self-driving car systems. In particular, we conduct our study on Apollo 5.0. So Apollo 5.0 is an open source self-driving car system that's mainly developed by Baidu. So Baidu is one of the largest tech giants from China. And in 2017, Baidu open source their Apollo system to attract some development from the community in large. And since then, Apollo has become the most popular open source self-driving car system that's available. And the slide shows from a high-level perspective that the programming languages that Apollo uses. So most of the Apollo is implemented in C and C++, which accounts for more than 500,000 lines of code. The second dominating programming language is Python, which provides some machine learning aspects and some data processing. And the third programming language or technology is protocol buffer. So protocol buffer is something that's developed by Google, which helps to encapsulate and serializing some structured data. So Apollo uses protocol buffer to communicate among different components, such as physical drivers and the software components, and to communicate among different machine learning models. And even though Apollo is open sourced, it actually has great and significant commercial impact. So Apollo is now providing some taxi services in several cities in China. So Beijing, which is the capital of China, is starting to offer some taxi services where the unmanned taxi is using the Apollo system. In this paper, we study in particular two aspects of the usage and integration of machine learning model and the source code. So we first look at how are the machine learning model used and integrated with the code. Then we want to study the dynamic aspects of the machine learning models and the code, where we study how well tested is the machine learning related code. So for the first aspects, how are the models used and integrated with the code? To study that, we follow a qualitative approach. So we try to manually study the system and the model architecture. So from Apollo, we first look at the documentation, as well as trying to search for different file extension that represent the model file, the machine learning model file that's been trained using various machine learning framework, such as Caffe, PyTorch, TensorFlow, etc. Once we identify the relevant files, so the files that may be using the machine learning models, we further conduct manual analysis to look at the code and to look at how the model is integrated with the code. And now the slides shows a very simplified overview of the Apollo machine learning model components. And in order for a self-driving car to make a decision, it needs to gather information from the real world. So for Apollo, it uses camera to capture and recognize the traffic lights and to detect where the lamps are on the road. So for lamp detection. Then Apollo uses LiDAR to capture different obstacles in the surrounding. So LiDAR uses laser beam to scan through the surrounding environments in order to construct a 3D point map between the car itself and the surrounding objects. So it tells the system how far away between the car and the item that's in front of the car. In order to provide more accurate obstacle detection, Apollo uses both the camera, the LiDAR sensor, and the radar sensor for obstacle detection. And once the obstacle is detected, the machine learning model will try to predict whether it's a bicycle, pedestrian, vehicle, or others. And now the models give us 3 different types of information. So the traffic light information, lane information, and the potential obstacle. These model outputs will be combined together into another machine learning component, which is trajectory prediction. So it will try to predict in the next few seconds, for example, how the pedestrian will move. So try to predict the future movement. And this is, in a nutshell, the general overview of various components and how the machine learning models are used. Then we also look at in more detail about the specific model that's being used. So first, for traffic light recognition, we found that there are actually 4 different machine learning models for these tasks. So it has one model to recognize where the traffic light is inside the picture, whether it's on the top right, top left, etc. Then for each type of traffic lights, it has one corresponding model. For example, the traffic light may be horizontal, then it uses the corresponding model to predict and to recognize the traffic light from that particular shape. For lane detection, there are also multiple models. So for lane detection in particular, there are several models where they are pre-trained using different machine learning parameters. And developers, they can actually replace the model by just changing the configurations. Interestingly, we found that these models are actually trained using different machine learning frameworks, such as Caffe and Paddle. And this can cause some maintenance overhead due to the need to maintain and update the model across different machine learning frameworks. And now for obstacle detection, there are actually 9 models trained using 3 different frameworks. And for each type of sensor, it has a corresponding model. And the result from this model combined, they need to then be used to choose which model should be using for trajectory prediction. And for trajectory prediction, there are 14 models for 9 different program points. And by program points, what we meant is that at a certain states of the car, we need to choose the corresponding model. For example, if a car is at the intersection, we need to find a model that's trained specifically for making decision when the car is at an intersection. We also found that many machine learning models, they have configurable threshold. So developers can tune the threshold. Usually the value is between 0 and 1 as a cutoff threshold, so that they can customize the model when making some decisions. So all the information combined makes the model interaction and the entire systems very complicated. To sum up, Apollo relies on multiple information sources and machine learning models to make different decisions. And we found that the same task may even contain multiple models, which complicates the integration between the models and the source code. Then we further look at how the models are interconnected in Apollo. And we found that most of the time, the output from one model is used as the input for another model. So there's a chain of the model making prediction together. So if there's one model that has some issues, the entire system may be affected. We also found that sometimes the results from several models may be post-processed together or combined in order to make better prediction results. And finally, there are some state machines implemented in the code to choose different model based on the current scenario. As we mentioned in the previous slide, if a car is at an intersection, then the corresponding model will be used. We also look at the code that's surrounding the model in Apollo. And we find that developers that actually try to provide some safety nets to the system and to correct the model outputs if anything abnormal is observed. So for example, developers may be filtering out some invalid outputs based on some domain knowledge and heuristics. So for example, if they detected that there's some traffic lights in the picture, but then the area of the traffic light contains some negative number, which is not likely based on some domain knowledge. In this case, they will filter out such invalid outputs. Another interesting thing that we find is that developers, they also use some algorithms to correct the model outputs. Especially, they often use different time-sensitive constraints to revise the model. So for example, if suddenly the model says that it cannot recognize the traffic lights, but then maybe the previous second it recognized the lights to be red, then it would do the inference and say that the current second the lights is also likely to be red. So this kind of model interaction shows a need for further research, especially from the software engineering aspects. What we find is that most of the existing research only focuses on unit testing each individual machine learning model. However, due to the complex interaction among the models, more research is needed for testing the quality assurance of different model integration and the system from a larger perspective. So for the first part of the study, we find that the machine learning models in Apollo, they are often configurable, interconnected, and safeguarded by different code logic. Then for the second aspect, we study the dynamic of machine learning related code in Apollo. So we try to run Apollo in a simulator. So the simulator will run the system based on some data that's been pre-recorded from actual test run. So you will have the information such as the pictures taken by the camera, as well as some information from LiDAR and radar. So what we try to do is to see when Apollo is simulating, we are running Apollo in the simulator, how the methods in machine learning related components will be executed compared to methods from non-machine learning components. So what we find is that during runtime, Apollo actually executes a lot more methods in machine learning related components. So 35.5% of the methods in ML related components are executed. However, only 3.5% of the methods in other components are executed. So it shows that this kind of machine learning aspects and machine learning components are especially important during runtime. Then we look at how the test coverage or how well tested is the Apollo system from their CI test perspective. So we look at branch coverage, line coverage, and function coverage. And in particular, the perception and prediction are the two machine learning related components. What we find is that perception component in particular has much higher test coverage compared to other components and prediction components. So we can see that developer, at least in the perception component, try to put more testing efforts. However, the effort is not enough. As we can see, the coverage is not very high. So it shows some evidence that more testing effort is needed in order to improve the CI test coverage in Apollo and to ensure the quality of the code. So we find that despite the importance and frequent execution of machine learning related code, the test coverage has still a large room for improvements. To conclude, we first talked about that software engineering plays a key role in AI powered system. Then we talked about or focus on on self-driving car system due to its importance and economical aspects. Then we first study the code from a qualitative perspective and represents how the models are used and integrated with the source code. Then we study the dynamic aspects where we look at the test coverage for the CI test cases and how the code is executed in a simulated environment. And thank you very much for your attention. So if you're interested in the paper, please visit my website and you can find the preprints there. Thank you very much.